Hello everyone, I'm Karthi Vignesh. In this video, we're going to talk about exercise number 5 in Object Operating Systems Lab, which is the classical problems of synchronization using semaphores. So we have three problems here in this exercise. The first one is bounded buffer or the producer-consumer problem. The second one is dining philosopher's problem, and third one is reducer-writers problem. So I already solved all the three questions. So I'm just gonna explain what the problems are, and we're gonna talk about the coding, and we'll see the results. So the first question is bounded buffer, which is producer consumers problem. This problem will be having a buffer and will be the main objective of this problem is to have the buffers to be um, like prevent the writers, the producers to produce content when the buffer is full, and to prevent the consumers from consuming the content when the buffer is empty. So I'll share you the code right now. So this is a code for it. I've written using the mutex, and in this one we have three options. First we have three options. The first one is producer, second one is consumer, third one is to exit, that is to stop the program. So when we give the value as 1, the choice will be to have a producer to execute the producer function. The function is written in the last. So in the producer function, what we are doing is we are essentially using the mutex, and we are printing that we have produced one item, and we signal the mutex. So the second option is to have the, and we are having a switch case here. This is to check whether the buffer is full or empty. If the buffer is full, it prints that the buffer is full, and in the case of like in the case of we choosing the consumer, and we're checking from the consumer whether we can consume anything from the buffer, and if we can't consume it, that means the buffer is empty, and we'll print it to the user, and then we are breaking the switch case. So that's basically it. That's how this program works. So I'm going to execute it now. So first I have a limit set as for the buffer as 3, so we can't produce more than 3 processes. So first I'm gonna try to produce 3 processes, and we'll be achieving the buffer full condition. So after producing 3 items, we can no longer produce any items. It shows that the buffer is full. So now I'm gonna consume the items one by one. The last item that we produce is the one that will be consumed first by the consumer. That's how the program works. It's basically like a stack. So as you can see, the consumer has consumed the item 3, 2, and 1. Now if you try to consume it, it should throw an error that the buffer is empty. As you can see, it shows that the buffer is empty. So the program works as intended. So I'm gonna exit it, and I'm moving to the next question. The next question is basically dining philosopher's problem. So here, a number of philosophers will be seated in a round table with some sort of food in front of them, and they will have two chopsticks on the either side of the plate. So what, I think we have a picture here. Okay. So what basically the problem is that only like to eat the food in front of them, they need two chopsticks, but so a philosopher can't eat if one of the neighbors is eating right now. So it basically causes a conflict there. This is for synchronization. We have to like synchronize it in such a way that the philosophers are able to eat in a time when the neighboring philosophers are not eating. So that's basically the main motive of this problem. So I'm gonna show you the code for it. I've solved it. So here I'm using threads, and I have used I've declared 7. Okay, I've declared 6 constants. Those are n for 5, thinking as 2, hungry as 1, eating as 0, and left and right as these values. These values are used in the calculations basically. So first we have a test function. This function is to check the whether the philosophers who are whether the neighbors of a specific philosopher is eating or not. This test will confirm whether a specific philosopher can eat or they cannot eat. So the next function is taking the fork. This is given that the philosopher is hungry, and we will be calling the test function to check whether the neighbors are free. If the neighbors are free, then he will have access to uh, both of the chopsticks near his table. No, sorry, near his plate. So the next function is the put fork function. The put fork function is basically used uh, after eating. The put fork function is used to drop the chopsticks to the table so that the next philosopher can pick it up for eating. And then we have a philosopher function. In this function, we are just basically going to, like, randomly take one philosopher to make them take the fork, eat it, and keep them down. So this is the main function. In this main function, I'm just creating n number of threads. The n is the number of philosophers. I have declared it as 5 in my program, and in this one I'm solving it in a way that only one philosopher eats at a specific time. So so yeah, it just has loops, and it just calls the previous function that we have declared already, and it uses mutex to solve it. I'm gonna execute the program now. Since I'm using threads, since I'm using threads here, I have to specify hyphen p thread for executing it, or else it will throw numerous errors. So this is basically an infinite loop. And first the philosopher 5 takes the forks and eats it. Then he puts down the fork. I'll stop the program. And he puts down the forks, and then the 5 is back to thinking. Now the 4 takes the forks and he eats it. And philosopher 1 takes the forks and he also eats it. 4 drops the forks, 4 is thinking. 3 takes the fork if available and he starts eating it. So this output is basically how it has multiple threads going on. That's why the philosophers are able to simultaneously eat. So yeah, that's how this program works. So moving on to the last question. The last question is readers writers program. So a database is shared among several concurrent processes. So we don't want to have conflict between a reading process and a writing process. So basically, we're just gonna do we're just gonna let the readers read and write when no readers is reading currently. This is to prevent the conflicts that usually happens in this type of code. So I'm gonna show you the program for it. So again, we are using semaphores and threads here to solve the problem. So this is the writers function, and this is waiting for a sorry. In this one, we are just trying to write it. Basically, we are accessing it as a writer, accessing some shared source as a writer, and this is the readers one. And in this one, we're checking whether the writers or right sorry in this one it basically checks whether any writers are active right now, and when a reader interferes the writer gets stopped. That's how this is the part where it gets stopped, and it means that the reader, whatever number of the reader that is reading currently. And then in the main program we are initializing the threads and semaphores, and then I'm having array for 10 array for 10 values, which is 1 to 10. This array is basically just the numbers for the process that we'll be using. Like, we are printing reader x is reading this, reader y is reader x is reading this, writer x is writing modifying this. So for that purpose, I'm just using this array as like just for numbering it, and I'm having four threads here, which basically creates the five number of it first. The first loop basically creates five readers. On the second loop, basically creates five writers, and then I'm joining each of the readers and each of the writer, and in the end, I'm destroying the mutex and the return. Sorry, and then I'm returning 0 because I've declared it as int main. So I'm going to execute the program now, and like the previous one, I've used threading here. So I have to specify pre-thread while compiling it, or else it will throw numerous errors. So this is the reader's output. So reader 1, 2, 4, 3 and 5 is reading, and the reader's count is always 1, and the writer's count is modified from 2, 4, 8, 16, 32, etc. So this program is also working as intended. So these are the three programs that are supposed to be solved in this particular exercise number 5. So yeah, that's it for today's video. See you guys in the next one.